Hello everyone. In the following, let me illustrate the property of variance for all of you. First one, variance of a random variable s, it should be non-negative. That says larger than or equal to 0. And for a new random variable, cx actually if we want to have for the individual x, and then we move the constant to the outside of the operator of variance, and so that we need to raise power to 2 for c. And next one, here we simply have the sum of random variable x. For sum of random variable x, and then we have the sum of variance if they are independent or they are uncorrelated. Therefore, we have the three properties. So right now, let me show you how to have the three properties. Well, first of all, the first property, variance of variable s greater than or equal to 0. Likewise, I use a continuous random variable to show you how it's valid. Alright, so how it's valid? So we can use the definition variance. And variance actually it's the square. So x minus its mean. So its mean raised power to 2, and here we have the PDF. Alright, and this one actually square larger than or greater than larger than or equal to 0, and this one positive. So finally, of course, larger than or equal to 0. So it seems to be trivial. So this is the first property. And second property, we have this cx. Alright, cx, how to have a cx? Same, follow the definition, it should be this. We have a cx minus this, expectation cx. And raised power to 2, however, for the final one, only PDF for variable x. And according to the previous property, we have this, it's constant c and expected value of x. So we have c and move c to the outside and to the outside of the interval. So we have this, it's x, and here we have this one. So finally, what's this? Actually, this is variance. So we have c squared and variance x. Alright, so this is the second property. And let me move on to the third property. Third property simply focus on this, variance for sum of variable x, xi. And then we will have the sum of the individual variance. Actually, we can have a constant c, and so that ci inserted into the expression, we can have a ci squared. But we still follow the current setting, just check the variance of sum of the individual random variables. Well, for this, under the condition independence or uncorrelated. Alright, independence or uncorrelated. And here I prove it for independence, and later, if necessary, we can prove it if they are uncorrelated. Well, so even independence or uncorrelated, either one, it still have the same result. So how to have this? we will have a variance equal to the definition again. We have a multiple integral, and this time we have this one, and expected value raised power to 2, but this time we should have a joint distribution. Alright, and for this, actually we can have the property first. This one, previously we have the property. Oh, it's the linear combination of expected value itself. And so this one can be rewritten to, oh, okay, we have this. I from 1 to n, and we have xi minus individual one. Alright, but it's square. Alright, and still follow the joint PDF. For this one, actually we have the result, but we have sum of the individual one. So sum of the individual one, we can have this. It's S1 minus mean. I use X1. Or maybe you can have the others. We have these 2. Plus this xn. Again, write it again. Why? Because we need to have the multiplication. Alright, so multiply is square. So currently, I just implement the terms here. However, we have n terms for the first expression, and likewise for this expression. And for this multiplication, so how to have the result? Oh, first of all, it should be this. Square. As for the others, actually, it's cross term. So cross term, how to have the cross term? This time it should be I from, actually I can have this, I not equal to 1, but we have the cross term. Right? I not equal to 1, but you need to multiply itself. So multiply itself. So wait a moment, let me have the results. It should be expected value first, sorry. Well, so something wrong? Oh, sorry, here it's summation. It's a summation. Alright, so currently it's a summation, sorry. So these. And likewise for 2. So 2 we have these. And likewise not equal to 2. And here we have these, but 2, 2. Here, this one cross term not equal to n, and this one is should be n, this. Alright, so the current term is summation. Alright, so right now multiply because we need to expand. So expand here, square, so expand, multiply, so that we have a square. And the terms here, actually we have the square term, so I use a different color. Square term, and square, and square. For all the square here, using the current manipulation, square term, the joint probability. Finally, what the term here can be, actually they are variant. So currently for the terms here, it should be variance. So finally we have variance, but later I will rewrite it variance. And for the others, actually they are cross term. Alright, cross term. So right now let me rewrite this. I erase the term here. So maybe let me move it back. So we try. So for the current one, actually we should have this. Oh, okay. One term should be this. We have a summation for I, expected value, and the square, and I from 1 to n, so the term here, and using summation. Alright, and so we have a brace plus the cross term. So the cross term, actually we should have this. Summation I not equal to 1, and xi multiply e equation xi, and multiply the first term. And likewise to the others. I not equal to n, and multiply xn minus this. So for the first one, for the term here and summation, so it should be variance. So we have variance xi, I from 1 to n, and multiply the remaining. The remaining, they are cross term, and cross term. So cross term, because of uncurrent or independence, they are 0. So finally, we have summation for all the individual variable xi. So maybe I follow the current description, and because of the limited space, I cannot explain in detail, but I show you they will be 0, and so that those terms vanish. Alright, so this is the property of variance. Alright, that's it. So about the property of variance, let me stop here and see you next time. Bye bye.